Hello everybody. In this video we are going to start with chapter 23, which is the second chapter in the mass transfer part in the textbook. And this chapter has the title of the differential equations of mass transfer. This is a pretty important topic, and it covers a part of the diffusional mass transfer that was not covered in the previous chapter. Before going into the details of this equation and the derivation and the mathematical part of it, I would like to take this video as an introduction to this topic. And I believe this is a very important introduction because this is not covered in the book in details. It just discussed very briefly. And I believe that if this introduction is not understood well, or this idea is not understood well, then this might cause some problems, or you might not feel why this topic is important. So to start, we have already discussed a good law that we used before to calculate the flux or describe the flux in the case of diffusional mass transfer. And this was Fick's first law, and the Fick's law is a good law. If I know the concentration gradient, then I can calculate the flux, and I know the concentration gradient in three dimensions, in x, y, and z dimensions. So it can be a 3D differential equation that can describe or can be used to calculate the flux in three directions. And this is correct. However, this equation will fail to describe the diffusional mass transfer in many cases. There are three main cases where this equation is not going to be helpful, and it's going to fail to describe all the parameters in the system, or all the things that's happening in the system. So one case is if we have parameters or concentrations that are changing with time. So if you take a look at this equation, you'll see that the flux is constant, and this constant flux is calculated based on only the concentration gradient, which is the change of concentration with x, y, and z. So if you have this equation, or use this equation, so you are assuming that the parameters are only function of x, y, and z. Or the concentration, is only a function of x, y, and z, which are the three independent variables. So time is not there. So if you have a case of unsteady state diffusion, which means that the concentration changes with time, so in this case you cannot use this equation to describe the diffusion, because there is no time dependence here. So this is one drawback of the equation. The second drawback is related to the cases where there is a reaction that's taking place while diffusion is going on, and this reaction leads to or results in the production or the consumption of the species that I'm doing the balance equation on. So the concentration is not changing only due to the difference in the concentration from point 1 to point 2. It is changing due to the production or the consumption of this species due to the chemical reaction. So if I have a reaction, then this equation is not going to help me, because there is no term here that says that this is the term that you use in case of a reaction. It's not there. So the equation is going to fail if I want to use or calculate the flux in case of a chemical reaction. The third case is that the concentration gradient here is an input to the equation. So if I want to get the concentration gradient as an output, as a product of this equation, then I cannot do this. So this is not gonna help me if I am interested in getting the concentration profile, how the concentration changes with distance at any specific distance. What is the concentration? This is not going to be an output of the equation. This is an input. So if I want to have this as an output, then this equation is not going to help me. So from this discussion, we can find out that this equation is not sufficient, and I need a more general equation. This more general equation should take into account all these cases. So This is why we are describing or discussing in this chapter the general equation of or the differential equation of mass transfer. So this is a general equation for diffusional mass transfer that I can use in any condition. So I don't care if there is reaction, if there is anything. So based on the discussion or the drawbacks of the previous equation, then we predict that, or we can tell that the equation that we are looking for should include some terms. One term is the time dependence, so I should have change or dependence of concentration with time. So it should include one more independent variable, which is time, and there should be a reaction term for production or consumption, and it should contain a term that allows me to predict or calculate the concentration profile. So these are the three main things that I am looking for in the equation, and these are my goals from this chapter, is to produce the equation that can give me all these outputs. And this is or these are the main 3 points, and we are going to check them later. So what we are going to do in the coming videos, like 2 or 3 videos, I'm going to make the derivation of the equation, produce the equation in the final form, and then I will come back and present the same slide here and see if these 3 points are satisfied, to make sure that the equation is doing what I want it to do. So before we go into these discussions, the differential equation, I can predict how the differential equation should look like. I can tell even before I start the derivation that there are some things that should be there. So I can do this based on my prediction and from my understanding of the similarities between heat transfer, fluid mechanics, and mass transfer. So I can tell that this is going to be similar to the differential equation that's used for fluid mechanics, which is Navier-Stokes equation, and the general heat transfer equation, which is the heat transfer conduction equation, which are all differential equations. And all the 3 are partial differential equations, and all the 3 have 4 independent variables. As we said, they should be time, x and y and z. And then the main difference between the 3 equations, of course there are some differences, especially for the Navier-Stokes equation than the heat and mass transfer. Heat and mass are similar in many cases, or in many ways more than the Navier-Stokes equation. But in Navier-Stokes equation, it is considering the independent or the dependent variables as the pressure and the rho v. In case of heat transfer, it's temperature. In case of mass transfer, it is concentration. So from this, I can tell that I will have partial C, partial T. So of course it's going to be a partial differential equation because it has more than one independent variable. So I'm going to have a partial derivative of C with T, with X, with Y, and with Z. It can be first derivative, the second derivative, whatever, but I should expect the partial C, partial X, or partial 2C, partial X square, whatever. The same for Y and for Z and for T. So this is something that I should be expecting even before I start. So I will stop here, and in the next video we'll start with the mathematics. The derivation is kind of it's not difficult, but it's nice to know, and it can give us an understanding of some of the points related to the equation and how we got these terms and what each term represents. And this is important because we will need this background in future problems that we will solve, so that we understand how we can substitute in the equation. So I'll stop here and we'll continue the next video, inshallah. So I'll see you then.